strong acid and weak base titration curve. The titration between strong acid with a weak base, for example here, weak base NH3 ammonia in conical flask, fixed volume, so it's in a conical flask, with 0.1 molar HCl in the burette. This is the strong acid, this is a weak base. Same molarity, fixed volume of ammonia. Initial pH, we need to calculate the initial pH before adding any strong acid into the conical flask that consists of ammonia. So now, initial pH of solution is the pH of 0.1 molar of NH3 because we only have NH3 in that conical flask. Since NH3 is a weak base, we know that it's not completely dissociate. NH3 very slightly dissociate in water to form OH- and NH4+. So the pH is based on that production of OH-. Very slightly dissociate. So 0.1 molar initially, ignore water because it's in liquid state, no production of product before the dissociation, and then change in NH3 negative X because 1 mole, 1 mole, 1 mole, so negative because it's if reactant decrease, the product increase, the product increase, so plus X at equilibrium, the concentration for NH3 0.1 minus X, OH minus concentration X, NH4 plus is X. Now we want to calculate the pH. pH equal negative log H3O plus, but we don't have H3O plus, we have OH minus. So for OH minus, we need to calculate the POH first. POH equal negative log OH minus, but we don't have the concentration of OH minus. In order to determine the concentration of OH minus, we need to calculate the Kb. Because Kb is given, use the Kb equation, product concentration over reactant concentration. So we can get this OH minus because the Kb value is given. So X squared over 0.1 minus X, so this one times 10 negative 5. So you can assume this X is very, very small. So assume that 0.1 is minus X is equal to 0.1, so X is negligible, X is extremely small, so we can ignore this X, and then Kb is equal X squared over 0.1 only, and we'll get the X value 1.8 times 10 to the power of negative 5, X equal 1.34 times 10 to the power of negative 3, so this is the concentration of OH minus. X is the concentration of OH minus. We can calculate the POH 2.82 and then the pH 11.18. At before any acid, at acid volume 0, the pH 11.18. Acid volume 0, pH 11.18. That's the initial pH. Next, after we add 5 ml of HCl into the NH3, so here we have weak base reacts with strong acid, there is neutralization process occur. So for the neutralization process to occur, we need to calculate how many more NH3 react with how many more HCl to get to know what's left after the neutralization reaction, because we need to calculate the pH. You can't calculate for each NH3 and HCl pH. We need to calculate what's left in the conical flask. So you need to take account the neutralization between NH3 and HCl, and then the buffer pair, it's between NH3 weak base and the salt of acidic salt, or this pair is conjugate acid pair NH4+. So you need to take account those two. Neutralization equation, the weak base and strong acid produce salt and water. So this salt is acidic salt. The equivalence point pH must be less than 7 at equivalence point, because this is acidic salt. Now, we need to calculate pH after adding 5 ml of HCl. we calculate the number of mole that is reacted between NH3 and H3O+, or you can write down NH3 and HCl. Okay, here HCl, and here you can write down NH4+, or the salt. Here, the number of mole that is reacted, we have the volume and concentration. You can get the number of mole. Here, the concentration of the acid and the volume of the acid. You can calculate the concentration of the acid. The concentration of HCl is equal to the concentration of H3O+, because HCl is strong acid, so strong acid completely dissociate to produce H3O+. So that concentration will be the same, and same goes to the number of mole, because 1 mole HCl will produce 1 mole H3O+. So when you have this number of mole, molarity, and the volume, you get the number of mole. That is the number of mole of H3O+ as well. Initially, there is no product at all, so 0 initial number of mole for NH4+, or here you can write NH4Cl. We calculate the number of mole of change. So negative, negative, this is our limiting reactant because it has less number of mole. So the reactant will decrease, so that's why negative product will increase, positive here. And then 0.002 is the number of mole of final. So it means in the conical flask, after the neutralization reaction, what's left in the conical flask are NH3 and the salt, or its conjugate acid. So we have weak base and conjugate acid. That's what's left in the conical flask. When we have the number of mole, we can calculate the concentration or the molarity of the weak base and the conjugate acid. So here the molarity 0.0167 molar of the conjugate acid, and the weak base 0.00667 molar. When we have the concentration of these two, because these two is what left in the conical flask, we can calculate the pH, because this is the buffer solution, the weak base and its salt. So this is buffer solution. For buffer solution, to calculate the pH, we use Henderson-Hasselbalch equation. POH equal PKB. Because we are using weak base, so POH equal PKB plus log salt over weak base, or you can put salt, or you can put the conjugate acid concentration over the weak base. So we have the value of Kb negative log 1.8 times 10 to the power of negative 5 plus log, this is the concentration of the salt or the conjugate acid, over the weak base concentration. It will get POH 4.35, and then pH equal 14 minus POH. This is the pH after adding 5 ml. Next, after adding 10, 15, and 20, if you calculate, that's how you calculate the one that you calculate after adding 5 ml, the previous slide. So you'll get the number of mole, and then you can get the concentration, and you can calculate the pH and then plot the points using Henderson-Hasselbalch equation to get this pH. POH equal PKB plus log the salt over weak base. Next, titration. pH after adding 25 ml HCl. Before this, we add until 20 ml, and then we add 25 ml. This is where the equivalence point at. Equivalence point is when this reactant of weak base, all weak base, react with all strong acid. So there is no more weak base or strong acid left in the conical flask. That is when the equivalence point at. So when we have 0.0025 mole weak base, we need to react with 0.0025 mole of strong acid, because it's stoichiometry 1 mole, 1 mole. So it will produce 0.0025 mole of salt and water. So here, at equivalence point, when there is no more NH3, no more HCl after neutralization reaction, because that's what equivalence point is, when all base react with all acid, no more acid or base in the conical flask, only NH4Cl and water, only the salt and water are in the conical flask. We need to calculate the pH when there are only salt and water in the conical flask. We know that water pH is 7, but our salt here, our salt is acidic salt. How to identify the type of salt? Look at the salt dissociation. So NH4Cl dissociate into NH4 plus and Cl minus. Now our NH4 plus undergoes hydrolysis. Cl minus does not undergo hydrolysis. Why? Cl minus is from strong acid. Strong acid, the anion or cation that is from strong acid does not undergo hydrolysis. But the cation or anion from weak acid or weak base, it will undergo hydrolysis. So this NH4 plus will undergo hydrolysis. It will produce H3O plus and NH3. When there is production of H3O plus, we call that salt as acidic salt because it produces H3O plus. So this is acidic salt. At equivalence point, we only have salt and water. Since this salt is acidic, so the pH at equivalence point is less than 7. This is how you plot the curve. Draw the point at 25 ml HCl. The pH is less than 7, slightly less than 7. Next, after adding 30 ml HCl, after we add 30 ml HCl, we calculate the number of mole of HCl. That is the number of mole of H3O plus. So 0.003 here, and H3 is 0.0025 mole. From 25 and 0.1, so you get 0.0025 mole. So only 0.0025 mole of NH3 will react with 0.0025 mole H3O plus, because this is the limiting reactant. Reactant will decrease, product will increase. And then there is no more weak base in the conical flask after this neutralization reaction of 30 ml HCl. So this here, H3O plus become the excess reagent. In the conical flask, after the neutralization reaction in the conical flask, there are only H3O plus and the conjugate acid, NH4 plus. So it's a mixture of strong acid and weak acid. Our conjugate acid is weak acid. This H3O plus is from strong acid, so this is a combination of strong acid and weak acid. And then in this region, H3O plus from reaction of NH4 plus means this here, we know that this is from acidic salt. Acidic salt, there is production of H3O plus. So here, acidic salt, we have the production of H3O plus. Strong acid, we have H3O plus as well. But in here, H3O plus from reaction of NH4 plus, means from the acidic salt, is negligible. We only take account the H3O plus from the excess HCl. So you ignore this number of mole of NH4 plus because this is the production of H3O plus. Ignore this because we don't take account this H3O plus from NH4Cl. We only take account H3O plus from the strong acid, not from the weak acid. So pH equal negative log H3O plus. We have the number of mole, so we need to calculate the concentration from this number of mole. Concentration is number of mole divided by the volume. Our volume now is 25 plus 30. 25 NH3, 30 HCl. Volume of solution 55 ml. It's 0.055 liter. This is the molarity of H3O plus from the strong acid HCl. Now pH equal negative log H3O plus, and you will get it 2.04 when the volume of HCl is 30. Next, you add 35, 40, 50. HCl will become the excess reagent, and then you calculate as before, pH equal negative log H3O plus, and you will plot the curve. This is weak base strong acid titration curve, pH versus volume HCl. So we start with at volume HCl 0, there is no HCl at all, only weak base, so the pH that we calculated is 11, and then after that we add the HCl at more HCl. In the conical flask, it consists of weak base and its salt. So here we call it buffer region. And then here is buffer region. And then here equivalence point. At equivalence point, pH is less than 7. When pH is less than 7, it means that the salt at equivalence point only contains salt and water. So when pH less than 7 means that is acidic salt in here, or weak conjugate acid or acidic salt. And then after that, after the equivalence point, we have more and more HCl, we have excess HCl, so no more weak base, so that's why the pH decrease after equivalence point. Initial pH starts above 7 because this is weak base. It's not like almost 14, that's for strong base. We are using weak base, so the pH starts slightly above 7, around 11 pH, because the weak base dissociates only slightly. And then the pH between initial and equivalence point here, around here, initial and equivalence point, the pH decreases gradually in the buffer region. So here, the conical flask consists of weak base and its salt, so that's why we call it buffer region. And then at equivalence point, the pH is less than 7 because it only contains, in the conical flask, only contains the salt and the water. That salt is acidic salt. That's why the pH is less than 7. We call it acidic salt or weak conjugate acid. And then after equivalence point, all HCl reacted with the OH minus from weak base, so no more weak base left, only excess HCl, so that's why the pH decreases. Suitable indicators. Methyl red is suitable indicator because it changes color on the steep portion. So here we use methyl red because the pH at equivalence point is less than 7. Suppose that methyl red is suitable. Phenolphthalein is not suitable. We don't use phenolphthalein for weak base strong acid titration curve because the pH at equivalence point less than 7. So from 8.3 till 10 pH, the color, there's no color change here because all buffer region. So all buffer region, it won't show any changes for phenolphthalein, only for methyl red. So how to determine the suitable indicator for titrations? Choose an indicator which the endpoint or the equivalence point pH range lies on the steep portion on the titration curve. This choice ensures that the pH at equivalence point will fall within the range. So you have to look at pH more than 7, less than 7. You have to look at that it must be within the range to determine the suitable indicator for titration. For strong acid, strong base, any indicator will be suitable except thymol blue. Weak acid, strong base, pH range for indicator must be between, the color change must be between 7 till 11, which is phenolphthalein or chrysal red. For strong acid, weak base, the pH jump is between 3 to 7 because we know that equivalence point is less than 7 for strong acid, weak base. So the suitable indicators are methyl orange, methyl red, chlorophenol blue, bromophenol blue.